everybody. Welcome to this class of fluorescence spectroscopy. The plan for today's lecture will be little bit about instrumentation, and then we will switch over to the topic fluorescence quenching. So, if you recall the last day's class, last day's lecture, in that case, I mean there we discussed these various aspects of instrumentation and important points, important parts related to instruments, like we talked about the basic design of a spectrophotometer and parts inside, like light source, different types of light source and their characteristics. Then we talked about monochromator, that is the inside of a monochromator. We discussed Czerny-Turner design, which is the commonly used design in modern spectrophotometers. If you go to the website of different companies like Horiba, maybe Hitachi, or maybe Perkin-Elmer and many other companies, you will be finding that this is the I mean the mostly used design with respect to the monochromator. Now, the thing is that in some cases double gratings are used, and in some cases only single grating is used. Okay. So, in order to achieve a better resolution, you need to further resolve the beam after it emerges out of the first grating. So, we discussed that one, and then we discussed in detail this detector, that is the photo detector, which is used in spectrophotometer, and maybe similar detectors like photomultiplier tube is also used in absorbance spectroscopy as well. So, and how this works, all these things we already have talked about. Now, today one important thing that we plan to just give you some idea that like modes of detection in this fluorimeters. One is your which is called the photon counting mode or the digital mode, another is the analog mode, or I mean it is not like the digital one. Okay. Now, the basic design of this is like you have got a PMT, and that is in I mean here in the left hand side it is the photon counting photon counting way of basically photon counting or the digital mode, and here it is the analog mode. Okay. Now, and here we have the PMT, and this is your light source, and this light source is accepted by, I mean the radiation or the emission is accepted by PMT, and there is a variable voltage supply depending on whether your intensity of emission is very weak or strong. If it is very weak, then you need to increase the sensitivity of the photomultiplier tube, so that you can increase the voltage, I mean the bias voltage against cathode and anode. Okay. And this anode current, that is pulse averaging, is fed into a computer, and then with respect to a wavelength drive, I mean we plot it, and that gives the signal, I mean the spectra which we get, and it is a continuous current measurement procedure. Okay. It is given to the device which takes the data. Okay. And in the photon counting mode, it has got a constant high voltage supply. Just recall this basic design of a time correlated single photon counting. I will come to that in a little detail, but before that just let me tell you what is happening. So, it is a constant high voltage supply, maybe minus 1000 to minus 2000 volts, somewhere around, I mean somewhere in between that, and you have to keep the voltage fixed, and you have got the PMT, then single photons are coming, or the photons are entering the PMT, and PMT gives out the signal, and there is a discriminator which which puts the threshold that whether you will receive the right signal or not, and then based on the discriminator setting, okay, the Ttl pulse, that is transistor logic pulse output. Okay. So, a Ttl pulse output, that means one photon is equivalent to one pulse. That way you just fade into your computer, give it to the computer, and computer saves those information with respect to time. Now, so this is basically, and it is very sensitive, and in other case for your analog system it has got a high dynamic range. Okay. Now, the basic description of a time correlated single photon counting, you see that we need to have a pulsed source, otherwise we won't be able to see the time course of the process, that is process of decay. Okay. So, so we have a pulsed source. This pulsed source may be pulsed like nitrogen lamp, that is a nitrogen flash, which is giving a train of pulses at some maybe some kilohertz or similar frequency. Maybe nowadays we use laser mode locked laser source for this pulsed light source, and depending on the type of laser that you are using, this pulsed light can be very short pulse, several femtosecond or maybe several picoseconds, or maybe several nanosecond as well, like in ND-YAG laser you can have like around 5 nanosecond pulse for say 1064 nanometer, that is the fundamental. But in this particular lecture we are not going into the details of this laser oscillation. The point is, if we get time, then maybe we will spend 1 or 2 lectures for discussing the basic principle of lasing action, because lasing is basically your light amplification by stimulated emission of radiation. So, it is also a emission of radiation, but the only difference is that it is the stimulated emission of radiation. Okay, go back to this pulsed light source for TCS-PC, which is time correlated single photon counting. So, you have got this train of pulses, and then it is fed into your sample. Okay. Then you need to have, depending on your requirement, either you can use a filter to chop your undesired frequency or undesired wavelength. So, filter is based on the fact that it allows certain wavelengths beyond its cutoff range. So, if it is a UV card, that means UV is not allowed to pass, only visible is allowed to pass. So, if you do not want to have UV photon entering into your detector, then you can put a UV cut filter. In the same way, other filters can also be available. So, so basically filter or maybe better, if you want to resolve in terms of wavelength, you can use a monochromator. Okay. And then you need to have a neutral density filter. Neutral density filter has the capability of reducing the intensity for the entire optical region. So, that is why it is called the neutral density. Just think of a just a goggles which looks like something like blackish in color, not exactly very dark, but maybe a blackish tinge. So, that is similar to neutral density. So, sun goggles, think of sun goggles, that when you wear the sun goggles of appropriate density, then maybe you can even walk in intense sun, because most of the photons or a large chunk of photons are cut off, so that you feel better, that is not many photons enter into your eyes. So, that is why you feel better. So, in the same way, depending on whether you need you have huge signal, so you can reduce it using the neutral density filter. Then in a PMT, that should be operated in photon counting mode, and you have got this it is called your constant fraction discriminator. There is another constant fraction discriminator. So, and there is a timing electronics, or there is a second PMT. This is your first PMT, and this is your second PMT. What is happening that this PMT keeps an eye on the first photon which is coming out of your laser or the pulsed light source. So, what happens is that the moment it receives a signal that maybe one pulse has gone out of the source and it enters into your sample compartment, then your this electronics is on. So, it gives a signal, I mean it gives a signal to which is called this TAC. TAC is time to average converter, TAC, time to amplitude converter, time to amplitude converter. So, it is given to TAC, and the moment this PMT, I mean the detector PMT receives an optical signal, that is when photon falls on PMT, then a signal is received by the second constant fraction discriminator, which says the TAC to stop. That way it occurs. So, and the time difference between this arrival of the first signal, this is your start signal, this is your start, and this is your stop. So, time gap between the start and stop is basically what we measure, and then it is fed into a ADC converter or a multi-channel analyzer, which puts your information as a function of different time gaps between start and stop, and that generates your histogram. So, what is the role of a discriminator? So, you have a discriminator, and it is special kind of discriminator called the constant fraction discriminator. Now, in case of normal discriminator, it would just trigger when the leading edge of the input pulse reaches a definite threshold. Threshold means it is a minimum value. If you have a signal which is above the threshold or just touching the threshold, then it starts to operate. Okay, that means it gives a trigger to the TAC. Okay, although here I am talking about this normal discriminator, but in case of constant fraction discriminator, what we generally use, you see that this constant fraction discriminator, this trigger is based on the PMT pulses, that is this PMT pulses, the CFD, that is the constant fraction discriminator at some constant fraction of the pulse amplitude, it is avoiding basically pulse height induced timing jitter. Okay. So, basically it triggers at some constant fraction of the your this pulse, I mean this laser pulse, or I mean the PMT signal. Okay. So, basically suppose if your PMT signal is something like that, then maybe at some constant fraction of the total height, it is said to trigger your this TAC. So, this way it operates, and what is happening now, basically this start signal is given to TAC so that it is turned on, and the stop signal is given to the TAC to turn it off, and it is basically TAC has a switched current source charging a capacitor. So, it is basically a capacitor charging mechanism, that the time required to charge a capacitor to some value. So, basically the principle works with remarkable accuracy, and a few picosecond can also be resolved by this charging mechanism. That means you have a charging ramp and you have got the capacitor. So, what you do is you measure how much charge is accumulated. So, that charge accumulation has got some time value depending on the time constant of that particular this LCR circuit inside this stack. So, that is now then converted to time signal. So, that means basically what it plots is as a function of charge, I mean amount of that is charge that is stored in the capacitor as a function of, I mean that is your time scale. Basically the amount of charge that is stored in the capacitor charging, I mean capacitor is directly proportional to the time. So, that is why it is plotting this amount of charge and this is the number of events. This way it is generating the photon counting histogram as a function of counts I mean as a function of, I mean as a function of time, and y axis is your counts. So, basically TAC gives this information to this multi-channel analyzer, and it puts the appropriate point in the multi-channel, I mean this plot with respect to, I mean with appropriate time information in the x axis. Okay. So, this is basically the these are the this is the histogram. This is like maybe this is delta t, say some lower value, then some another value. So, you see that this data has been piled one after another, so that it gives you the idea that maybe at this time gap maybe many, I mean most of the events are occurring, and maybe this time gap very few number of events are occurring. That means you can say that maybe this corresponds to say 100 signals, I mean 100 pulses, this corresponds to say 10 pulses or maybe 50 pulses, like that, and this way you generate the histogram. So, in order to have more information, you can I mean a detailed account of this, still having more detailed account of this, you can consider or consult this principles of time correlated single photon counting by O'Connor and Phillips, and another book by advanced TCS/PC I mean technique by Wolfgang Becker. So, these are the two books that you can consider. So, this is the basic mechanism by which you get this time information against the number of events, and then you, with the help of proper deconvolution procedure, you can find out the components that are there, that are there in a given decay process. Okay. So, this is about, and again it is another block diagram with a laser as a source, that it is a DPSS pump laser, although I have not talked about laser, but think that it is a source of pulsed light with maybe very short pulse, I mean full width of maxima very less, so that you can, I mean you have the opportunity to follow faster events, I mean events which are of the order of maybe several picoseconds, or even I mean in that range. So, Millennia 10 watt DPSS diode pumped solid state laser, pump laser. There is a Tsunami femtosecond Ti-Sapphire laser. It is a special kind of Ti-Sapphire oscillator, titanium sapphire oscillator. Then these are some other things. Then I mean the various types of pulse shaping, or and pulse selector device. Then ultimately pulse is given to the sample chamber, and you see that there is a synchronized, I mean there is a part of this pulse has been fed into the photodiode, or maybe what I call as PMT2. So, this puts to the discriminator 1, I mean this photodiode pulse is given to the constant fraction discriminator. It is based on the it triggers at some constant fraction. So, you can change it depending on your necessity. And this trigger is based on this photodiode pulses. So, discriminator 1 puts this start, and sample chamber, then via monochromator there is PMT, then amplification, and then given to the discriminator, and it provides you the stop. Okay. And this is TAC, time to amplitude converter, and then this is pulse height analyzer, or multi-channel analyzer, and ultimately given to the computer to give you this photon counting histogram. So, this is quite interesting method, and depending on the signal intensity, I mean fluorescence intensity, sometime I mean in some experiments you will be finding that maybe it takes about maybe 5 to 10 minutes to get sufficient counts, and the point is that you need to have sufficient count because it is a statistical averaging procedure. So, if you have more sample, then your answer, I mean your experimental result will be more accurate and will be more acceptable. So, that is why you need to have sufficient number of counts, I mean maximum count, maybe it can be 10,000 count or maybe even more than that. So, the more the number of maximum number of counts, the better will be the possibility to get I mean higher will be the possibility to get better result. Okay. So, I mean this is very important. So, this way you can find out the radiative lifetime of the excited state, and the point is as I told you in earlier lectures that the decay of the excited state generally follows I mean it follows a first order kinetics, but in some cases if more than one species are involved in the decay process, like say one is your locally excited emission and say another is some converted, I mean suppose if this locally excited state undergoes some specific alteration that it gives emission, but at some different frequency, or maybe it gives emission in the similar frequency range with different time constant, then your data will not be basically a single exponential one. The term single exponential means if you plot basically log count, it is generally plotted as count versus time. If you plot log count versus then time information, if it is single exponential, then it will be it will be basically a line. But if it is not single exponential, I mean it is if it is a multi exponential, then you may expect like something like maybe it will deviate from linearity. Suppose if it goes like this and then something like that. Okay. So, in that case it will be not exactly linear with respect to log count. So, but the point is in that case you can expect more than one more than one time constant. So, more than one time constant corresponds to this different two different processes, but the point is you have to get corresponding other information, so that like other chemical information, like whether this species has got the possibility to undergo some other in modified form, like say form 1 and form 2, like that. So, that you have to check from other information, and accordingly you can analyze and you can interpret your data. So, this is interesting. As far as time result studies are concerned, it is very interesting. And if this can be extended, this study can be simply extended to with the help of this pair of analyzer, polarizer and analyzer to this sample chamber, before the sample chamber and after the sample chamber, and accordingly depending on the relative orientation of your this excitation polarizer and emission polarizer, you can get information of this IVV, IVH and other things that is required to calculate this anisotropy of a sample. So, basically the same apparatus you may be using, but only thing is that in that case you need to put a pair of polarizers. Okay. So, that will that will get you anisotropy related information and experimental data, and from that you can find out the anisotropy decay and other related issues. Okay. Next we move on to a topic which is called fluorescence quenching. Now, before we start this topic, we should have the ideas of different processes that are occurring when an excited state is generated. And generally if you consider regular molecules, regular means or commonly available fluorophores, then you will be finding that their ground state is electronic ground state is singlet, okay. And very rarely, it is very rarely we will be encountering with a species with triplet state, triplet ground state, like oxygen is a triplet, having a triplet ground. Anyway, we are not going into the what will happen for a triplet ground state right now, but let us start from a singlet ground state. So, what is happening that when you excite with appropriate frequency, then the molecules will switch to the excited state, and depending on the lifetime of the excited state, it may undergo several processes. And why I am talking about lifetime, because of the fact that if say if it stays, or if its lifetime is less, if it stays for very less time, then it may not get sufficient time to undergo the secondary processes like intersystem crossing or something else, or maybe some other mechanism of deactivation. So excited state lifetime is very important, and when you do some fluorescence measurement or fluorescence lifetime measurement, then the point is that you need to have if you want to go for triplet measurement and if you want to go for singlet measurement, then for singlet measurement you may not need to think of this impurities like oxygen, because oxygen is a triplet, ground triplet. So, that ground triplet creates trouble. But when you are interested in looking at this triplet state, then you have to be very cautious. Why you have to be very cautious? Because oxygen is a triplet quencher. So, if you are unable to remove oxygen from your solution, from your cuvette, okay, from your cuvette means this is the this is a typical cuvette that we generally use for your emission measurement. You see that all the 4 windows are open, and this is different size cuvette. So, when you put your sample in the cuvette, and if you are interested in looking at this triplet state, then you have to be very careful. You need to remove oxygen. So, what you do is you bubble your solution with argon, that is you saturate argon for maybe half an hour, okay, slow bubbling of argon gas into your solution, that is solution containing fluorophore. And then what you do, you take the measurement, you seal the container with appropriate sealing agent, and then you take emission. So, you will be seeing that if you do not de-aerate, degas, it is called degassing procedure. So, if you do not degas your solution, then triplet intensity, the phosphorescence intensity will be very less, but the point is fluorescence intensity will not be affected, or will be very little affected. Maybe if other contamination is there, or maybe some other related phenomena is occurring, then maybe a little bit, there is a little bit chance of alteration of fluorescence intensity as a result of degassing. So, why fluorescence? The point is the fluorescence is not at all affected with triplet quencher, because of the fact that triplet quencher quenches by means of collision, and since singlet lifetime is very short compared to this collision frequency, that is why what is happening that fluorescence quenching, fluorescence intensity is not affected by triplet quenchers. But the point is, if you add some other agent from outside which has got the tendency to undergo collision, collision with the excited state within the lifetime of the excited state, then there is a chance that this excited energy may get transferred to this colliding molecule or colliding species, and emission will be reduced. So, if you increase the concentration of this, if you increase the population density of this quenchers, these are called quenchers of these external species, then you will be seeing that emission intensity is progressively reduced, and also lifetime of the excited state is also is affected. So, so that is this phenomenon of quenching is quite common, and this is one of the important way to study different things, like the behavior of the excited state, and maybe other issues like studying interaction of species, fluorescent species with something else. Okay. So, various things can be followed with the help of this fluorescence quenching technique. So, basically quenching, if we look at the general photophysical processes, then some chemical reactions are initiated through photoexcitation. Their kinetics will depend on the rate of formation of the excited state, that is very important. And excited excited state forms via absorption of a photon. The excited state is depleted through a number of processes, fluorescence, phosphorescence, internal conversion. So, fluorescence, phosphorescence, these are radiative, internal conversion, and maybe intersystem crossing, etc. These are non-radiative. The reactivity of the excited state molecules depends on how quickly it decays. So, if it decays quickly, then there is a trouble, but if it stays for considerable amount of time or considerable interval of time, then there may be there may be possibility of reaction. So, steady state approximation has been applied to the excited state species because that is metastable. So, we are applying steady state approximation. I am coming to that in detail. So, this fluorescence lifetime is expressed in terms of Kf, that is radiatory rate constant, and then internal conversion rate constant and intersystem crossing, singlet intersystem crossing rate constant, and from this we can find out different things. So, now what is quenching of fluorescence? So, whatever I told right now is basically all about what is going to happen after photoexcitation, various possibilities, and of which fluorescence quenching is one. Okay. So, there is a related term, Stern-Vollmer equation, that always, this is always uttered when we talk about fluorescence quenching. This term is always uttered. This Stern-Vollmer equation. Now, if the excited molecules are deactivated and the fluorescence is reduced, then phenomenon is called quenching of fluorescence. It is a non-radiatively, fluorescence, suppose initial fluorescence intensity is 100 unit, and suppose because of something, because of deactivation, that deactivation may be due to your quencher, that is external agent, or maybe due to something else, maybe increase of temperature or something else. So, suppose initially your fluorescence intensity is 100 in some unit, and say it is reduced to 50, then of course this will be termed as fluorescence quenching, or if all other factors are remaining constant. Only one factor, like if you are adding something from outside, or maybe you change the parameter like temperature, then it is this phenomenon is called quenching. When the excited state undergoes a change from singlet excited state to triplet state, then it is called the internal quenching, that is internally it is quenched, because if the triplet is not emitting. And when the activated molecules or the excited molecules collide with other molecules or quenchers which are added externally, and they transfer their energy to them, then this is called your external quenching. So, external quencher and internal quencher, these are the two terms, associated terms. Okay. So, we should always remember in terms of these two things. Okay. So, besides normal decay process like Kf, that is fluorescence, fluorescent radiative rate constant, then Knr, that is Kic and Kisc. So, basically if you think of like this S0 then S1, then this is Ia, then Isc, then this is P and this is F and this is IC, internal conversion. So, this is Kf, and together with this if we call that as K inner, or maybe it is KIC, and this is KISC. Okay. So, overall rate is Kf plus KIC plus IC, that is Kf plus KIC plus KISC, together these two is called Kf plus KNR, that is non-radiative, Kf plus KNR. Okay. So, and in addition to that, if you have a quencher, then it is basically a bimolecular process. Okay. Bimolecular process means like it I mean to have this process, you need to have a excited species and a quencher that quenches. Maybe it may occur in a collisional mode, or maybe by some other mode. Right now we are not going to talk, going to give you the details of it. Okay. But we need to have two things. One is this excited S1 plus your quencher, this is Kq, it will give you S0 plus quencher back plus maybe heat energy. Okay, that is energy is used up. Okay, so that means it comes back to the ground state by maybe collision with this. Okay, now and what we have to have is other processes are like one is Kf, another is KIC, another is KISC. Okay. So, KF means your S1 giving rise to S0 plus nu H nu F. This is KIC S1 S0 and this S1 to maybe to T1. So, if we consider all this, only thing is that this rate will be equal to Kq into S1 concentration into Q concentration. Okay. So, it depends on this S1 and Q quencher concentration. So, that means you have this if you apply steady state approximation to all these species, like your S1 is generated via IA, rate of formation of this S1 is, so S0 to S1 rate of formation of S1, that will be equal to, only channel is that where this is formed is IA, that is intensity of it, because intensity means number of photons entering per unit area per unit time. So, IA, and so here it is formed and remaining rest is depleted. So, minus Kf into S1, then minus KIC into S1 concentration minus KISC into S1 minus KQ into S1 into Q. Okay. So, if you apply steady state approximation, then you can get like this S1 concentration will be equal to IA divided by Kf plus K NR means sum of these two, plus Kq into Q. So, this is S1 concentration. Okay. So, that means so then in that case your if this is not there, then how to write your fluorescence rate constant. Okay. So, in terms of fluorescence lifetime, what you can write is that 1 by, so if we consider all this, then 1 by tau f 0, 0 means in absence of any quencher, that will be, that you can write like k f plus k n r. Okay. And in presence of quencher 1 by tau f q, that will be basically you can write like k f plus k n r plus k q into q. Okay. So, you have got two expressions over here. Now, how to write your this quantum efficiency for this one? So, you can write phi 0. Phi 0 means in absence of any quencher. So, simultaneously you have to consider the case when this quenching process is there. In one case quenching process is there, and the second case quenching is not there. So, this one tau 0 means when quencher is not there. So, q equal to 0. So, phi 0 you can write k f by k f plus k n r, it is the ratio of this radiative rate constant divided by sum of all the rate constant, and phi, this is f 0 and phi f q, in presence of q you can write k f is there always, then k f plus k n r plus k q into q. Okay. So, if you now divide these two, then what you are going to get? If you divide these two, then you have phi f 0. So, dividing those two, dividing these two. Okay. So, dividing these two, what we are getting, let us see. So, phi f 0 by phi f 0 by phi f q will be equal to. So, that means phi f 0 means you have this k f by k f plus k n r, n r contains as I told you both, into k f plus k n r plus k q into q divided by k f. Okay. So, that means k f is gone. So, basically you have 1 plus k q into q divided by k f plus k n r. Okay. Now, what is this basically? What is this? This 1 by k f plus 1 by k n r is basically, you can write 1 plus, this is your 1 by this means this gives you tau 0. So, that means tau 0 means lifetime in absence of any quencher. So, k q into q, and you can call this as a new constant 1 plus k s v into q. So, this is called the Stern-Vollmer constant. Okay. So, this Stern-Vollmer constant contains your radiative lifetime in absence of any quencher and the rate of bimolecular quenching, rate constant for the bimolecular quenching. Okay. So, it is given, and in detail. So, let us check it. Whatever I just told is written clearly. The presence of a quencher Q, a channel for deactivation of S star means S1 is opened. So, this deactivation channel is written like this. So, rate in presence of quencher, quenching process rate is k q into q into S star, that is a singlet state concentration then what you have to have is you have to apply this steady state approximation with respect to S star. So, this I absorbed means the rate at which it is produced, this S star is produced, and remaining are is now depleting. So, therefore, Kf S star, Kic S star, Kisc S star and Kqqq S star, and that will be put to be equal to 0. And from that we have to find out this S star concentration, and using this S star concentration we can just calculate this fluorescence lifetime. I mean, we can express fluorescence lifetime in terms of this. So, when this Q is absent, then it is simply in absence of quencher, and when Q is present, then in presence of quencher. And this fluorescence quantum yield is basically what I told you, K by Kf plus Knr plus Kq into Q, and ratio of phi 0 and phi q is then given by 1 plus Kq tau 0 into Q. So, this is the this is what? This is your quantum yield in presence of quencher and in absence of quencher. So, you see that if you can now plot phi 0 by phi q as a function of quencher, then what do you expect? So, phi 0 by phi qf, that is fluorescence quantum yield, you have a plot like this with intercept equal to 1, okay, and this slope will give you Kq into tau 0. If you if you have the information about tau 0, then from this slope and this tau 0 you can find out Kq, that is the rate constant for the bimolecular quenching process. Okay. So, that is why this is a very useful and handy expression, very simple and handy expression that gives you the idea of gives you the idea of this Kq, this rate of bimolecular quenching constant, and this is called the famous Stern-Vollmer expression. So, this is Stern-Vollmer expression or Stern-Vollmer equation. So, the idea is that if an additional deactivation channel is opened up as a result of this external agent like quenchers, then if you include that into the entire into the rate process of deactivation, okay, rate process of deactivation of the excited state, then you end up with this expression that phi 0 by phi q, or generally in many books you will be finding just phi 0 by phi. That way you can write phi 0 means in absence of quencher and phi is in presence of quencher. Okay, so now if we using the same argument, you can write, so phi f 0 by phi f q is equal to, since intensity is proportional to quantum yield, so you can write f 0 by f. So, if you monitor fluorescence intensity at some wavelength in presence and in absence of quencher, then you can get the similar plot. So, basically the plot will be f 0 by f as a function of quencher. So, you can generate like these data points and just you connect with line, then you should be able to find out this Ksv, this slope will be equal to Ksv, that is the Stern-Vollmer constant. And from this you can also write tau 0 by tau, that is the lifetime in absence of quencher and in presence of quencher. Okay. In absence of quencher and in presence of quencher, you can get the similar thing like tau 0 by tau. So, if you can monitor this lifetime, radiative lifetime in presence of quencher and in absence of quencher and as a function of quencher concentration. Suppose you do the experiment with variable concentration of quencher, that you make solution in different container with having 0 quencher concentration and next having some added quencher, then you plot either tau 0 by tau or f 0 by f or phi 0 by phi, then you will be getting this type of plot. Okay. So, that is the basic idea, but right now we are not going into the details of exactly what is the mechanism of quenching. It may be just giving you the idea, it may be simply this collisional process or maybe some other complicated process, maybe some interaction which is not exactly collision, but maybe some interaction that gives you quenching. So, these complicated issues will be taken up, but before that common mechanisms of bimolecular quenching, I am giving you this just idea, that is, one is collisional deactivation. Okay. And S star plus Q giving S plus Q plus is particularly effective when Q is heavy species. Heavy means like heavy atom like iodide, bromide or something like that. Then it may be resonance energy transfer, that S star plus some quencher, then S is given, S star plus Q, then Q is excited, Q becoming Q star plus S is deactivated. So, it gets deactivated and it gets excited. Okay, this way it is happening. Maybe electron transfer. So, S star plus Q, then electron is transferred either from S star to Q or Q to S star. Okay, excited S, and then new species is generated which is having less fluorescence. So, fluorescence quantum is reduced, and as a result of which you get less emission. Or maybe the other option could be which I have not written over here, that it may be some complex formation which is called the dark complex. Suppose you have got your fluorescent molecule like this and you have another species which makes a complex with this in this way, so that basically this combined one if it does not fluoresce, which is called a dark complex. So, ultimately what we are getting? We are getting that initially it was fluorescent, now it is less fluorescent. So, it is also a quenching process. So, this may also happen. This is called a complex formation. So, all these detailed issues I will be back with in the next lecture. So, what we have learned today is just basic, one is the remaining part of the instrumentation, that is the this digital and analog mode of data acquisition in fluorescence spectroscopy, and in application of digital acquisition, this photon counting mode for time collated single photon counting studies, and then we started with this giving you the idea of this fluorescence quenching, and we have just deduced this famous Stern-Vollmer equation. So, in the next class we will take up other issues which we have not talked about over here about this fluorescence quenching. So, so that is all for today. So, till then, till we come for this next lecture, have a good time and see you back. Thank you.